Okay, let's look at the Excel example of application of the goodness of fit test, chi-square test. We in previous video we went through some light theory. Now let's look at the example. But before we go there, I'll chart the map, right? What are we going to do? Well, we'll generate the numbers from beta distribution. We'll generate the numbers from beta distribution using those inverse CDF techniques, which we learned in other videos. But then the question is, okay, I generated these numbers from beta, but how do I know that they are actually from beta distribution? What if I made a mistake in my formula somewhere and the numbers are not from beta distribution? How could I test that? Well, one way to test that would be I would take these numbers and then build a histogram. All right, so I'm showing it here. And then I would compare that histogram against the, let's say, a known PDF of the function. And when I say known, because I'm using beta with the following parameters, 2, 2, and then I went to Wikipedia, you see those are in purple line. So look at this purple line. It looks like an arc. So I'm expecting the histogram to look like an arc. And it does look sort of like an arc, but not an ideal one. So I could maybe decide that, you know what, it looks like an arc. Well, maybe it is a beta after all. But there are many distributions which will look like an arc, and maybe it's too tall or too wide or whatever, right? So it sometimes is desired to have more formal technique of testing. It's not always better to have a formal technique, I would say. In some cases, it's actually not a good idea at all. But it's good to have that tool in your tool set in case you need it, right? So and here we are going to use it. So okay, well, visual examination of my histogram shows that yeah, it's close to the arc. Now let's apply, oh, by the way, this is a CDF, cumulative distribution function histogram, and it also looks kind of like this purple line, right? So how I'm going to do it statistically? Well, I will first create the histogram here, which I called simulated, and then I will compare it to theoretical frequency, right? So I have 1,000 numbers, and in each bin, each of these 10 bins, I will say how many should be there theoretically, right? Expected numbers. Then I'll compare them versus the actual or observed ones from my column B. Then I'll do the test statistics and compare it to critical value. So in this case, you see that test statistics is not greater than critical value, which is great. It means that the deviations of my observed from expected are not that big, right? So which means that maybe I should accept or I should not reject my null hypothesis, which is that my numbers are coming from beta distribution. Let's look at the example. So I'm going to press F9 several times, but before I do that, I'll just show you what's going on in this column, right? It is the same technique, inverse CDF technique, which we studied in other videos, but in this case, I'm applying to beta distribution with the following parameters. Alpha and beta equal to, and as I said, in this case, I should expect a arc-shaped histogram. And I built the histogram from what? From 10 bins. So I have 10 bins, and in each bin, I counted the number of observations from my column B, right? If you see, I'm getting the column B, and then I'm calculating the number of observations. And then I'm calculating in the column K frequency. That would be my histogram column, which I'm showing here, right? I'm showing the number of generated numbers in each bin. So they add up to 1,000. That's great, right? So it means that I'm using all these 1,000 numbers. It means I counted them properly. I hope so. So if I press F9 several times, you see my histogram, right? Histogram is dancing a little bit, right? It's changing, but it's sort of preserving that arc shape. So I have hope, right? So it looks like it probably is beta, right? Maybe my code was correct. So after all this inverse CDF business, maybe it works. But as I said, the next step is let's calculate, let's do it formally through chi-squared statistical test, right? How are we going to do it? Well, we need theoretical counts. We need ease, right? From this handbook formula, ease, expected ones. Where are we going to get them? They're in column H. How did I calculate them? Well, first I calculated, this is not good. Naming is important, right? Because it's not PDF. Okay, in column D, I'm calculating the CDF at the right edge of the bin. So look at this bin. This bin is from 0 to 1. And to remind you, the beta distribution, didn't mean to move it, the beta distribution, right, is from 0 to 1, spans from 0 to 1. It generates numbers from 0 to 1, and all my numbers are actually from 0 to 1 here. So it's easy, right? I can get 0 to 1 and divide it into 10 bins. I didn't have to do it exactly this way, but I did it this way. So binning is on you. You have to figure out your own binning. What's important in my case is that in my bins I'm expecting not less than 9 counts, right? And that is sort of a rule of thumb, right? When you're designing your bins, you hope that the number of expected number of observations will not be less than 9. A rule of thumb. It's not like a law or anything, but just follow it. It'll save you from some trouble, right? So what I'm doing is here in column D, I'm calculating the CDF at the right edge of my bin, first bin. My first bin is from 0 to 0.1. All the numbers which are from 0 to 0.1 are going to be in this first bin. And I'm calculating CDF at the right edge, which, and then for in line 4, row 4, I'm calculating CDF at the right edge of the second bin, which is from 0.1 to 0.2, 0.1 to 0.2. Now you see for the second bin, I have a CDF at its left edge, which is right edge of 0.1, right? Because your second bin spans from 0.1 to 0.2. So now I have a CDF at left edge and right edge, which means now I can calculate the difference of CDF. And the difference of CDFs will be in which column? Well, actually here I am doing PDF. But let's ignore column E, right? So I'm using column D, but then in column H I'm calculating the expected frequency. How many observations I'm expecting will fall into this bin. Easy, right? So what I'm doing is I'm subtracting the CDF at right edge of my second bin, and from it I'm subtracting the left edge, and now I know I have this difference of CDF, and that is the probability that the observation from beta distribution will be in the second bin. Then I multiply it by 1000 because I have 1000 numbers. So once I've done that, this gives me in row 4, H4 cell, right? This gives me the expected number of observations in the second bin, the bin which spans 0.1 through 0.2. So you see I have 28, 76, 112, and so on, right? And these are the numbers which I'm going to subtract from observed ones, right? These are observed numbers. So it happens so that let's generate a few times. So for instance, in this case, it happened. Wow, it's an interesting case, by the way. Right. It happened so that in this set of random numbers in column B, I had 29 observations in the first bin, while I was expecting 28. So in column L, I'm going to accumulate my test statistic, right? So what I do, I take the deviation, right? I take 29 and subtract 28, so deviation was 1. So there was deviation was 1, I square it and then divide it by expected 28, just following the formula from the handbook, right? This is the formula. It's formula which was derived by Carl Pearson, by the way, very renowned statistician. Right, so I got this square deviation and scaled it by expected number, by expected observations in cell L3 for the first bin, and so on. I just go through all 10 bins, and then in row 13, L13, I'm summing it all up. And when I summed it up, my test statistics was 4.79. That is the chi-square test statistic. Once I got 479, I have to compare it to critical value, and my critical value is in cell L17. How did I calculate it? I just followed this formula from the handbook, right? What do? Well, I take chi-squared inverse of chi-square and then get 1 minus alpha. You see, it's actually written here in the formula. It's chi-square 1 minus alpha, right? So what is 1 minus alpha? It's 0.95 because my alpha is 5%. So that was the first argument, and the second argument was what? K minus C. K is number of bins, C is number of parameters. Number of bins 10, number of parameters 2, so K minus C will be 8. And when I calculate the critical value, what do I get? I get something like 15.5. Well, for this set of random numbers in column B, my test statistic was 4.79, and it is not greater. It's smaller than my critical value. And remember, what is this test statistic? It is the sum of squared deviations, which means that my deviations were not big enough from the theoretical distribution, which means it's good, right? So my numbers in column B, they look like they're coming from the beta distribution with these parameters. So what's interesting, if I generate a few more, from time to time, my it won't be very often, but sometimes, let's press so many times, because it's random numbers, right? It's a random sample, and anything can happen in the sample. And sometimes what happens in this sample, look, it doesn't look that much like an arc, and my critical value, my test statistics is actually greater than the critical value. So in this case, if I followed my formal testing approach, I would have to reject the null hypothesis. And null hypothesis was that columns in B are from beta. So unfortunately, I would have to reject them at 5% significance. I guess that was it in terms of the example. What else? I wanted probably, well, there was this 1 point p-value, right? So this test statistic, you can calculate the corresponding p-value, and the p-value will it's another way to test the hypothesis. So in this case, my p-value is less than 5% significance, which means I can reject my hypothesis. It means that the probability that this test statistic is too extreme is too small. It's smaller than 5%. So it's another way of comparing the critical value of the test statistic, right? What do you need to be careful? I want to bring this up because it's not emphasized in the handbook, and most textbooks will not talk about it, is the importance of saying specific distribution. It's a very important note. So if you were estimating your theoretical distribution from the data and then running chi-square test, it wouldn't be a good test. You can't do that. In this case, I knew that my distribution is with this parameter. I didn't estimate parameters. I knew them in advance, and then I compared my distribution against these. If I were estimating these parameters from my random numbers themselves, then this kind of a goodness of test cannot be used as is. You have to make some adjustment. And that was it.